Okay, so this video is to talk us through how we can get from our definition of change in entropy here for some infinitesimal change in entropy to an expression for delta S that goes between two states at known temperatures and volume. So we want to get from this expression of an infinitesimal change to a change between two states. So a delta S between state 1 to state 2, where our state 1 is at T1, V1, P1, say, and our state 2 is at T2, V2, P2. Okay. So basically, another way of thinking about this is that we would like to get this expression to something that we know how to integrate, right? So if we imagine integrating from state 1 to state 2 ds, that's going to be our delta S. And then we need to also integrate from state 1 to state 2 dq reversible over t. Okay. Now, quick point about that why it needs to be the reversible q in this change in entropy ds. Remember that the q, the heat associated with going from state 1 to state 2, is not necessarily the same for every path, right? The energy and the work are different for each path, but entropy is a state variable, and so we need to have the entropy of the two states not depend on the path that we take between them, and so it wouldn't make sense to use anything other than the reversible heat, since that's the only one that's going to be the same for every path. Even if you don't take that path, the energy associated with it is still going to be Q reversible. Okay, so we want to get this dq reversible term to be something that we can actually deal with and actually integrate. So to do that, we want to recall our statement of the change in internal energy from the first law. So that tells us that the change in heat plus the work done on the gas from a reversible process is equal to here. So then we've got dq reversal minus p dv. So no matter what reversible process we choose, this will be true. Okay. Now, remember as well that d and E internal is our CV dt, right? And that's true as well always, no matter what process we're actually taking. That expression for change in E internal is always true. And we're also going to substitute that P equals nRT over V. And the reason we're going to do that is that if we look at this expression here and we see our dV, it would be more convenient to have anything multiplied by that expression in terms of V, so that we get closer to something that we can actually integrate. Okay. So now we will solve this equation for dq. Okay. So that's dE int plus P dV. We're going to make those substitutions that we just talked about. So that's dq reversible equals dc equals cv dt plus nRT over v dv. Now, you might be a little bit worried about this, and appropriately so, that there's this t term here multiplied by dv, because that is not a constant, right? So the things we have multiplied by dt, this cv, that's a constant. The n and the r are constants. The v is in terms of the dv. So that one is going to be okay to integrate, but that t term is going to be a problem because it's not a constant. However, What we're actually trying to do is plug this into our expression for ds, which remember is dq reversible over t. So once we do that, we will find that we have cv dt over t plus nr over v dv. So luckily that t canceled out, and now this looks like something that we can actually integrate, okay? So again, we're going to integrate from state 1 to state 2 ds. That gives us our delta s. And then we're going to integrate from T1 to T2 for the temperature part of the integral, and from V1 to V2 for the volume part of that integral. Again, this is the same as doing this whole integral from state 1 to state 2, but we only have to worry about the temperature changing for the temperature part, since that's the only thing that depends on, and the volume changing for the volume integral that only turns on the volume. And so then this will give us, when we do this integral, CV T2 over T1 plus NR log V2 over V1, okay, is the change in entropy. All right, and of course the second term, we talked about the source of that one in class. The first term is harder to explain from the microscopic picture that we talked about in class, but this expression overall accounts for the change in entropy from changing both temperature and volume. Okay.